idea for today's webinar is to present the 5 conversion technologies that are being developing in the CAD-Converse project. My name is Pablo Morales. I'm the Communications Manager in Sustainable Innovation, and I'm also in charge of the communication and dissemination of the CAD-Converse project to make sure that we disseminate the project outcomes that have been developed. And as part of my task, one of the main activities is to organize several webinars to showcase the work that our technical partners are developing. And for today's webinars, the idea is to present the 5 conversion technologies from CO2 to chemicals. So the speakers are as follow. So me as Pablo, then we will have the opportunity to listen Rosen on behalf of EBIAP. And then I will give the floor to Mariana, who will explain the first technology from CO2 to glyoxylic acid. Then we will move to Tom, who will explain from the second technology from CO2 to lactic acid. And then we will have like a short interactive break conducted through Mentimeter. So make sure you have your phone next to you, since I will be asking you some preliminary questions to know a little bit more the audience. And then Eva Maya will present the third technology, which is from CO2 to furan dicarboxylic methyl ester. Eva Maya works at in Spain in the SIC Center, Research Center. Then Dulce Muñoz from Funditech, which is our coordinator entity, will present the fourth technology, which is from CO2 to cyclic carbonated acid methyl esters. And we will finish with Maria Anderez from Cartif, who will explain the last technology from CO2 to bio-methanol. Then you will have the opportunity to enter your question through the chat function in Zoom, where we will be able to answer all your comments, thoughts, or any doubt that you may have during the webinar. Some notices, the webinar is being recorded, so we will share this recording probably next week. Make sure that your microphone is muted. This is more for the speaker in order to not to have any audio issues. And as I said, have your phone next to you for the Mentimeter activity. And if you have any curiosity or something you would like to learn more about the CAD-Converse project, let us know in the chat function. Having said that, I think it's time to present the first speaker, Rosen. If you can briefly introduce yourself and start your presentation, the floor is yours.
Hi, this is Associate Professor Dr. Rosen Dimov, and I'm presenting on behalf of EVIAP. I'm sorry that my colleagues were not able to join today, as they're the domain experts, but it's a very big public holiday today in Turkey and the rest of the world, Eid Mubarak. I think I'll try to give you a gist of what we are doing within this project, and happy to take on your questions after that. So I'll keep the presentation short, and then, sorry, wrong window, but we'll share the right one now, and we'll be able to go through the following points of the presentation. First, we'll do an overview of what EVIAP is all about. Then we'll tell you about the lactic acid and glyoxylic acid, so they will appear as LA and GA in the next slides. We'll speak about the tests and safety assessment for all the cosmetic products that we are planning to develop within the project using these two acids. We'll cover the regulations, and you will also see a list of references that you could visit later on. First, it's the biggest cosmetic company in Turkey with nearly a century of history, but now a global brand that has production and R&D facilities in 3 different countries. And it exports to over 100 countries around the world. So if you haven't used EVIAP branded products, you could check in the local shop. I'm sure you'll find it. In the facilities, you could see, and we welcome you also to Turkey to check up all of these different areas where the products are developed and then produced. and we also have facilities in other countries such as Malaysia. Within the project, we have LA and GA used as chemical building blocks for cosmetic products. And we are focusing on 3 products: hydrating creams, body lotions, and shampoo for the pilot. And then we'll see which of these flies with the customers and try to explore the opportunities of commercializing one or several of these products. The GA is used within these products to increase the effectiveness and as a buffering agent in rinse of cosmetic products. This improves the stability, efficacy, and safety in the formulations, considering the wash-off effect afterwards. The LA, or the lactic acid, has potential within these products to be used with antimicrobial effects as a disinfectant, as a buffering agent, as a skin conditioner, and also as a humectant to add this humidity effect and keep it over time. The preliminary results that we'll provide within the project will show the benefits, how we could use it, and this is also pretty aligned with EVIAP's overall strategy of decarbonization, which you could imagine as a global company is very important, not only for us, but for the rest of the world. And this will create also new jobs. We estimate 4.5 million euros by 2030 when these products start entering the global market, and a lot of effect across the whole value chain. So it's not only what we do that will be beneficial for us and our clients, but also for our suppliers that will start making more carbon neutral and negative raw materials to supply to us. Then you could see here the formulation of the lactic acid and some of its basic characteristics, how it's used in our case in the personal care products, but it could be used for animal feed and food products. You could see already a product that we have in the market containing this, and this is the active X with the ingredients, and also you could check it online for the full formulation and how it's made. Then when it comes to the GA, you could see the formulation as well, and its synonyms, also the basic characteristics that it's used to brighten the skin, to have anti-wrinkling effect, as a humidifier or humectant, and to increase the production of hyaluronic acid. We have the different tests related to cosmetic products that contain these acids, and these tests will be done within the course of the CAT-Convert project, the stability tests, the microbiological enchant test, to really confirm that the products that we developed with these acids have all of these effects that we are really aiming for and claiming. We also have the safety assessment in line with the EU regulation 1223 dated 2009, and we need to confirm that this is safe for children and adults using the norms that are prescribed in the safety assessment. So here a few additional regulations that we need to observe and comply with when we develop these LA and GA based products at the EU level and at the national level. And of course, this then goes to the target markets that will eventually decide to enter with these new products containing La and Ga. And for additional references, you could see this list, could take a screenshot, or the presentations will be available after the webinar. And of course, after all the presentations, you could ask me questions, and I'm happy to help you with it. Thank you very much.
Thank you so much, Rosem, for this quick introduction to EVIAP and its role in the CAD-Converse project. Now I would like to give the floor to Mariana from Avantium. She will explain us the first technology, the electrocatalytic conversion.
Just share my screen. See if it works. Okay, are you able to see it, Pablo?
Not in full presentation. Click on the.
And now?
Now we can.
Yeah, okay.
Perfect.
So, good morning, everyone. I work at Avantium as a scientist in the electrochemistry group, the Volta group. And Avantium's role in CAD-Converse is mainly on the development of the electrocatalytic conversion of CO2 to glyoxylic acid. There's a lot going on in CAD-Converse. We work on many different technologies, so we don't have much time today to explore each technology, but I hope that by the end of the presentation, you will have at least a general picture of what we are doing in this project. So first, a very brief introduction about Avantium in case you don't know the company. Avantium is based in Amsterdam, and it's a chemical company that works on the development of sustainable processes for the production of chemicals from bio-based materials. The most well-known business unit is the renewable polymers, but we also have R&D solutions. The foundational technical expertise on catalyst testing comes from R&D solutions. And I'm coming from the Volta group, and in Volta, our focus is on the development of an catalysis platform to produce high-value chemicals. And with this, we hope that we can unlock CO2 as a new carbon source for the chemicals and plastics industry. So in Volta, our focus is on the electrochemical conversion of CO2. And why the electrochemical conversion? What are the advantages? First of all, it uses electricity as a renewable energy source. So it makes use of electrons as reagents to perform the redox chemistry. And this means that it doesn't require the use of high energy reductants or oxidants to perform the chemistry. So in general, we can say that it's a clean technology. It's flexible because depending on the demand for energy, we can adjust for the production rate. It's selective because we can tune the potential, and by doing that, we can prevent the over-oxidation or reduction. And in terms of scalability, it has a low risk because we don't need to increase the size of the reactors. We can just stack multiple electrochemical cells, and that can help reducing the risk of scaling up. Now, focusing on the production of glyoxylic acid, the industrial route for the production of this chemical is via the oxidation of glyoxal with nitric acid. And also prior to this step, there's also the oxidation of acetaldehyde, also with nitric acid, and acetaldehyde is a fossil-based chemical. So this means that for both steps, we need nitric acid, and the production of nitric acid requires a lot of energy and also emits CO2. And then if we look at the overall process for the production of glyoxylic acid, it also emits high amounts of nitrous oxides that need to be removed, and that step also requires a lot of energy. So what we propose to do in CAD-Converse as an alternative route is to start from CO2 released from biorefineries. We take CO2, and then with two electrochemical conversion steps, we first make oxalic acid, and in a second electrochemical step, we have the production of glyoxylic acid. So this is a process that starts from bio-based CO2, and it is also high atom efficient. In cat converse, we look at two electrochemical steps. It is well known that for these electrochemical conversion steps, lead electrodes are very efficient. They are very selective for the production of both oxalate and glyoxylic acid. So one of the main goals in cat converse is to look at alternative electrodes that can replace lead materials, and that's what we are doing within the project. And of course, you want to find not only an alternative electrode to replace lead materials, but these new materials, they should also perform as good as lead. And that's why we are targeting Faraday efficiencies above 95% and at current densities of at least 100 milliamps per square centimeter. In the case of the second step, the oxalic acid reduction takes place in an aqueous medium in a divided cell. And typically, the anodic reaction is the water oxidation. But in cat converse, to make this process even more efficient, we are also looking at replacing the water oxidation reaction by the oxidation of ethylene glycol to glycolic acid. And this means that in the same electrochemical reactor, we can make two valuable compounds, glyoxylic acid at the cathode side and glycolic acid at the anode side. Okay, so what does it take to go from lab scale to pre-pilot scale? In this project, we started as a first step with all the lab scale research, and here we were looking at electrocatalyst synthesis, the development of analytical methods to quantify the products, but also the side products that we could be forming in both electrochemical steps. And then we were testing different electrodes for each conversion step. Here in these pictures, you can see the electrochemical cells that we use for the electrode screening. The first one is used for the CO2 reduction to oxalate. The second one is a divided cell that we use for testing the oxidation of ethylene glycol. After we identify the promising electrodes for each reaction step, then we move to step 2, and here we start testing the reactions in a flow cell configuration, because that way we can mimic the conditions that we will have at pre-pilot scale. We also look at the optimization of the reaction conditions, mainly to increase the concentration of glyoxylic acid in the product stream. And then we need to assess the compatibility of the single electrochemical reactions, because when we combine them in the paired electrolysis configuration, we need to make sure that we have the most suitable membrane, that we don't have any problems with the different current density that is applied for each reaction, or also we need to check for the compatibility of the pH for the different electrolyte solutions. Then in step 3, we collaborate with EasyTech, and here the focus is on the design and manufacturing of the unit, the electrode and reactor upscaling. We also look at the process automation, hazard and operability analysis. It's important that we can safely operate these large units, because it's a step here to go from lab scale to operating these units. And of course, the final phase is to test the reactions at industrial conditions. And here we are mainly looking at impurities that might be present in the CO2 coming from the biorefineries. Okay, looking now at the integrated process to go from CO2 to glyoxylic acid, we have a first electrochemical step to convert CO2 into oxalate. And here we make use of sacrificial anode made of zinc. So we produce zinc oxalate. Then there's an acidification step and a zinc recovery step that is already done at industrial scale. And then in the second electrochemical step, we have the reduction of oxalic acid to glyoxylic acid, and this reaction is paired with the ethylene glycol oxidation. And then the target in cat converse is to test glyoxylic acid in cosmetics, and this will be performed by EVIAP. And to be able to do this, we need to make sure that glyoxylic acid has a purity of at least 95%. And here it's crucial to have the collaboration of EMI, also one of the partners in cat converse, because they will be looking at the development of a technology based on membrane separation to make sure that we can achieve this purity for glyoxylic acid before it is tested by EVIA. So for the downstream processing of glyoxylic acid, the goal is to achieve a selective separation of glyoxylic acid from the product stream and to get a purity of at least 95%. And ME20 is looking at two-step electrodialysis approach. So this is because the components we have in this stream, they have different molecular weights and different pKa's, so we can separate them using two electrodialysis steps. So we start from an aqueous solution of glyoxylic acid, our product. There's some oxalic acid that does not react in the electrochemical conversion step. And there could also be some glycolic acid present that can be produced as a side product. In the first electrodialysis step, we can separate oxalic acid. Oxalic acid can be recycled back. It can be fed back to the electrochemical reactor in the second step. And then in a second electrodialysis step, we have the separation of glyoxylic acid from glycolic acid. Of course, this is an iterative process and we collaborate with ME20. During the process, during the project, we observed that we could actually reduce the production of glycolic acid, and that also made things quite easier for the downstream processing because we are able to have a good separation between glyoxylic acid and oxalic acid with one electrodialysis step. Okay, and now just to wrap up, of course, to accomplish all these goals, we need a multidisciplinary partnership because we need expertise from different partners. I didn't mention in this presentation, but it's also crucial in CAD-Converse that we do the assessment of the environmental impact and the economic feasibility of these new technologies. And for that, we have the partners Nova, Alchemia Nova, and Dana working on it. So by the end of the project, we will have a good basis to compare our technologies with conventional technologies. And of course, to take the technologies to the next level, there needs to be a combination of efforts from research centers, academic institutions, and industrial partners. And I think we are doing it very good in CAD-Converse. Thank you for your attention. If you have questions, I'll be here to reply to them at the end of the webinar.
Thank you so much, Mariana, for this presentation. So I think now we can move to the next technology, which is from CO2 to lactic acid, presented by Tom.
Yeah, thank you, Pablo. My name is Tom Ewing. I work as a scientist at Wageningen University and Research in the Netherlands. And Pablo, will you share my presentation?
Yes, give me a
as we agreed.
second.
Yeah.
You let me know when you want me to move the slide.
Yes.
I guess you can see it now, right?
Yeah. Yeah. Could you go to the next slide, please?
Yes.
Okay, so I will introduce a technology where we're working on an enzymatic technology to produce L-lactic acid from carbon dioxide, among other starting materials. So yeah, this was already introduced in the presentation by EVIA. Lactic acid, it's an alpha hydroxy acid. You can see the structure here. And it's currently produced by the fermentation of sugars from biomass using bacteria. And it's used in cosmetics ingredients, as we heard earlier. But it's also an important building block for the bio-based polymer, polylactic acid. And particularly for this application, also the purity of the lactic acid in terms of the enantiomeric purity is important because this is important for the polymer property. So it's interesting to make a single enantiomer of this compound. Could you go to the next slide, please, Pablo? So in CAD-Converse, we will use enzymatic methods to capture CO2 and incorporate it in lactic acid. And what are some advantages of doing this? So first of all, The advantage of using enzymatic technologies is that they're often very selective chemically, getting few side products. The reaction conditions are typically quite mild, so in terms of pH and temperature and pressure, but also requiring few harsh chemicals, and enzymes themselves are non-toxic, biodegradable, and biodegradable. And also using enzymatic catalysis can give you some good possibilities to couple multiple reaction steps in a single vessel, as we call a cascade reaction, which we'll also see later. Some challenges that can be associated with this are sometimes there's a limited substrate scope, so you might develop a technology for one molecule that's not applicable to other very similar molecules. Kinetics can be slow compared to traditional chemical processes. Also, there can be some challenges involved with ensuring that the enzymes are stable under industrial conditions. Their production is cost effective, and particularly specifically for the conversion of CO2, often the thermodynamics of such reactions are quite not so favorable. If you could go to the next slide, please, Pablo. So what exactly are we working on then in CatConverse? So the idea is to have a 3-step enzymatic cascade to convert ethanol, which can also be produced by fermentation of sugars, or nowadays increasingly also technologies that we developed to produce ethanol from fermentation of gases, such as carbon dioxide. And we want to take ethanol and together with carbon dioxide convert it to L-lactic acid. And this is done in 3 steps. You can see them here. First of all, the ethanol is oxidized as acetaldehyde. Then there's a carboxylation reaction where CO2 is coupled and you get pyruvate. And this is subsequently reduced to lactate by lactate dehydrogenase. And this last step requires us to regenerate the NADH cofactor, which is used by this enzyme because it's too expensive to use in stoichiometric amounts. Now, there were some previous reports on this type of system, but they reported rather low final product concentrations of up to about 250 micromolar. And with our system, we would like to try and improve this. Next slide, please. So one of the first aspects that we actually worked on is to try and develop improved methods for this regeneration of the NADH cofactor that I mentioned. So this is a very expensive molecule. You don't want to add it in a stoichiometric amount. And there are ways in which it can be regenerated that are already well established. For example, using a second enzyme which oxidizes glucose and thereby regenerates the cofactor. But this has a disadvantage that you always use a second substrate and generate a second product, in that case, gluconic acid. So it'd be great if we could use hydrogen gas, for example, for the regeneration as the electron donor, rather than something like glucose. And one way in which you could possibly approach this is using heterogeneous chemical catalysis. So we actually explored this. We made various heterogeneous catalysts and tested them for the hydrogenation of NAD+ to regenerate NADH. And we got some catalysts that work well for this reaction, but the main challenge that we see is the selectivity. So we have various isomers of the NADH which are available, only one of which is accepted by enzymes. And using this heterogeneous catalysis is a challenge to really selectively produce this enantiomer. So with the best performing catalysts we designed, the selectivity is about 65%, which is quite good compared to what is known for this type of reaction, but it would need further requirement to be able to practically apply it. So for the rest of the project, we focus on using one of the established systems based on the oxidation of glucose by glucose dehydrogenase to regenerate the NADH. Next slide, please. So then we started focusing on developing the biocatalytic cascade. And one of the first steps in this was to identify new enzymes to use in this, and particularly to identify new pyruvate decarboxylase enzymes. So the enzyme that catalyzes the crucial step in the cascade and also the biggest bottleneck, which is the carboxylation of acetaldehyde, the pyruvate. And Johnson Matthey in the UK, one of the other project partners, worked on screening novel pyruvate decarboxylase enzymes that would have improved reactivity for this reaction. So they screened 31 enzymes in the end, some of which were already known from literature, others of which they identified as new enzymes using their bioinformatic techniques. Well, to cut a long story short, we found one very promising candidate enzyme, PDC20, which showed good reactivity for this carboxylation reaction that we're after and that we used in the rest of the work. Next slide, please. So we then took this PDC-20, this novel enzyme with good properties, and we used it to actually develop the catalytic cascade system. So there we're doing reactions in pressurized reactors, as you can see in this slide, because we have carbon dioxide as a reactant, so it can be beneficial to perform the reaction under an increased pressure of carbon dioxide. And then so far we've developed the reaction steps separately. So for the ethanol oxidation, we have achieved this at about 50% yield. Yeah, it can be higher, but in the end, we want to integrate the cascade into a full cascade where all the reactions occur in one pot. So the individual yield of this reaction then is not the most crucial thing to optimize because it will be converted further. We've also, for the conversion of acetaldehyde to lactic acid by carboxylation with CO2, achieved a 65% yield from starting material to a starting concentration of 10 millimolar acetaldehyde. This maybe seems not so high. It's a 6.5 millimolar yield, but as I mentioned before, the yields that were known for this reaction were significantly lower. So it's actually quite a good improvement. So what have we learned? We've learned that coupling this carboxylation reaction to the subsequent reduction of pyruvate to lactic acid is a very important thermodynamic driving force for the reaction. If you just try to do the carboxylation reaction in isolation, it will not work. And at the moment, we're investigating the full integration into a one-pot, three-step cascade reaction to have all the steps in a single pot. Next slide, please, Pablo. So then, yeah, if you could just click another 3 times, maybe, Pablo. Yeah, once more. Okay, so at EMI Twente, also in the Netherlands, another project partner, they're then developing downstream processing methods to isolate the lactic acid formed from the reaction mixture, which is quite a complex mixture. And that's based on membrane separation processes. And you can see the scheme that they use here. So they do a number of different steps. The first is using an electrodialysis step that removes all the non-charged compounds from the reaction mixture and leaves us only lactate, which is charged, and gluconate, which is the co-product formed from the NADH regeneration system. Then they need to separate these 2 molecules from each other, which is done by a number of nanofiltration steps. So that gives you a lactic acid stream. This is then concentrated using a reverse osmosis strain. And then the final step is to convert the sodium salt of the lactic acid, which you then have, to the actual acid form, which is done by a technique known as Donnen dialysis. And the goal here is to achieve lactic acid in a purity of 95% for application testing. Next slide, please. So I hope that I've shown you in conclusion that we were able to produce some novel heterogeneous catalysts for NADH regeneration, but that further increases in selectivity are required for practical application. That we identified a novel pyruvate decarboxylase with very interesting enhanced activity for carboxylation reactions. That we demonstrated the enzymatic carboxylation of acetaldehyde with significantly increased product titers compared to literature. That we can use membrane-based separation technique to purify the lactic acid from this complex reaction mixture. And I think that for future, an interesting outlook is to further improve and identify new enzymes for this type of reaction to further widen the scope of reactions that can be catalyzed with this type of enzymatic carboxylation chemistry. So next slide, please, Pablo. And that's just the final slide. So I'd like to thank everybody who was involved in the work from all the various partners. And thank you for your attention.
So much, Tom. Okay, so it's time to have like a quick interactive break. So I encourage you to participate in this short interactive activity. So I don't know if you have used Mentimeter before, but these instructions are very easy. So first of all, grab your phone and then go to the www.menti.com and then enter this code. I will give 1 minute. I will copy this code in the chat so you can have it also. And now I think you still can see my screen, right? Yes, because you are participating, so I guess yes. Okay, so the first question was, since we want to know a little bit more about our audience, is what country are you from? And we see people from several EU countries: Netherlands, Spain, Belgium, Italy, Netherlands, even Brazil, Greece. Okay, so quite interesting. Even Thailand, Austria, Sweden. Okay, good to see. I think we can move to the next question, which is, what industry do you work for? In case you are from the chemical industry, research, academia. Research, academia, chemical industry. Okay, so it seems in engineering company, most of the people seems that are from research and chemical. We also have oil and gas industry. Okay, nice results. So next next question is, what conversion technology are you most interested in? So we have listened the first two technologies. We're still missing to listen a few more, but before the webinar, we would like to know what was the most interesting conversion technology. So the CO2 to lactic acid is winning, now all of them. Also CO2 to bio-methanol. Okay, good to see the results. So it seems that most of you are interested in general in all of them. Lactic acid is competing with all of them. Okay, nice. Thank you for your answers. The last, I think it's the last question is, how did you hear about the webinar? Since we have been promoting from the newsletter, social media. Also, we encourage the consortium to share this event, mouth or mouth, and others. It seems that for now, the social media has been the most effective activity strategy. Okay, so good to see that the the social media campaign was having an impact. I think this was the last question, if I'm not wrong. Oh, no, there is one more. How will you rate the content of the webinar for now? I know that we are still missing some presentations, but for now, we would like to know if this is interesting for you. Yes, don't be shy. I mean, in case you don't find it not interesting, it's also good to know why are we not being so engaging or catchy. This help us to improve the next webinars. But it seems for now, most of you find the webinar very interesting or interesting. So this is a very nice feedback. Okay. Okay, so this was the last questions. I think it's time now to move to the next presentation, which is Eva. But since Eva is actually having some issues with accessing, Dulce, I will like to move to your presentation. So if you can share your screen. Oh, sorry, Eva is here.
Yes.
Sorry, is here. Sorry, I was not seeing. Hi, Eva. Finally, we managed. You are muted now.
Yes, I'm ready.
Perfect, perfect.
Can you hear me well?
Yes, if you can speak louder now.
Okay, yeah.
Yeah,
Maybe.
perfect.
Can you hear me better?
Better, much better, much better.
I think you have shown my presentation because I don't have access, right? Because
Okay.
I am not
No,
panelist anymore.
I can share it for you. You are panelist, you can share.
Okay.
But if you want me, I can share for you. No problem.
Thank you very much because
I was worried because we were having some connectivity issues.
yes, it was terrible today.
Okay, so here you are, Eva. Perfect. So can you see the screen, right?
No. I can see my presentation. I can see everybody here, but not the presentation.
Second. Okay, what about now?
Yes. Now this is the last one. Can you please the first one?
Oh, sorry. Yes. I thought it was
Okay.
the first one. Sorry. Here.
I think I need you pass my presentation. Okay.
Yes, no worries. You let me
No
know
worry.
when.
Okay.
Yeah.
Okay. Good morning. Thank you, everybody to join us. Okay, I'm going to explain a little bit about the technology 3 of CAP Converse, which is devoted to the synthesis of furan dicarboxylic methyl ester using CO2. Next slide, please. Okay, this technology has been done in the Superior Council of Scientific Investigation, the SIC, which is the main public research center in Spain. But specifically, this technology has been developed in the Institute of Material Science of Madrid, which is located in the Autónoma University campus. Next slide, Pablo, please. As I mentioned, the goal of this technology is the synthesis of furan dicarboxylic methyl ester, which is this molecule you can see here. Of course, using CO2 as a main feedstock, but also using furfural. Furfural is this bio-based molecule, so it's very interesting to have this monomer because at the end you are going to have a monomer which is bio and CO2 base. So our mission in this project is this conversion. Next slide, please, Pablo. The next partner in the consortium, Ava Biochem, is going to convert this monomer into bio and CO2 polymer, which is a very interesting application. Next slide, Pablo, please. Well, the main difficulty in this technology lies in the fact that the position 5 of the furfural molecule is where the CO2 must to be coupled is very, very deactivated. So to try to join CO2 to this position is the really hard part of this technology. The speed of this after almost 3 years, of work. Next slide, please, Pablo. We achieved this conversion, but the conversion requires some steps. So first, in a steel reactor, you have here a picture of the reactor. We introduce furfural and also a very strong base. In this case, cesium carbonate. And then we introduce oxygen in the reactor. After heating several hours, the oxygen must to be removed, and then we introduce CO2 in the reactor. And also we heat for several hours, and at the end we obtain this intermediate you can see here in the slide. It's very important to remark that these two reactions, oxidation and carbonization, were made with the same copper catalyst and without solvent. It's a solvent-free reaction. Well, we obtain this intermediate that, as you can see here, is an organic cesium salt, but we don't need to isolate this intermediate. We can follow with a next step. So next slide, Pablo, please. In this point, we need to remove the copper catalyst by adding methanol to the solution, so with a filtration. And when we have the copper catalyst out, next slide, please, Pablo. We made with the final steps of the process. First, we need to add some drops of sulfuric acid because we come from a very strong basic media. So we get a pH of 7 neutral conditions, and then we made the last step of the process, which is an acid esterification using methanol heating for some hours, and using also an acid catalyst. So in these conditions, we obtain the target molecule, the furan dicarboxylic acid, with moderate yield. The most of the success of this process, of course, are the use of the two catalysts. Next slide, please. So I am going to speak now briefly about how we prepare these two special catalysts. So I'm going to start with the copper catalyst. Next slide, Pablo, please. Okay, the copper catalyst was prepared in two steps. In the first one, the monomer that we can colloquially call salen was reacted without any solvent, using a new strategy called mechanochemical synthesis. Can you please, the next slide, Pablo? Here you can see a picture of a rotary mill. Is this apparatus when you introduce the monomer in a vessel, and the vessel has three. This is the reason because the symbol of mechanochemical synthesis is the three balls, because you use a vessel and you introduce the monomer and also three zirconia balls. And after mechanical stirring, you obtain a hypercross-linked polymer, a very nice network, very stable, that we call HCP salen. Next slide, Pablo. After we have this cross-linked polymer prepared, we introduce the copper. So the only thing to do is to mixture the cross-linked polymer with copper salt by heating, and the copper goes inside of the network, because this monomer of this polymer, has like a tetradentate linker to join the metal very nicely. Next slide, Pablo, please. The second catalyst is an acid catalyst and is prepared also in two steps. In the first step, we use these two monomers, aromatic monomers, pyrene and dimethyl chloride benzene, and we use also mechanochemical synthesis. We prepare this network. In the second step, Pablo, next slide, please. In the second step, we introduce the sulfonic acid groups using a regular sulfonation reaction, very common in organic synthesis. Pablo, next slide, please. The success, as I mentioned, of this technology is the use of these two catalysts. These are the responsible of the development of the technology. So the most notable things of these two catalysts are, of course, both of them can be prepared by mechanochemical chemistry, which is very nice because it's a very sustainable way to prepare catalysts. Also, they have very high thermal and chemical stability, and both of them are very, very selective to the corresponding conversions. And of course, they can be recycled. So in this moment, the process was made after 5 consecutive times without losing activity or with the same yield of the target compound. Well, this is a very quickly summary of the technology 3 developed within the CAD-Convert project. Next slide, Pablo. So only thank you very much for all of you for attending my presentation. Thank you very much.
So much, Eva. I'm glad we fixed these connectivity issues just in time. So now we can move with the fifth technology presented by our coordinator entity, Funditech. And Dulce Muñoz, who is the technical coordinator. So Dulce, the floor is
Yeah.
yours.
Thank you very much, Pablo. Can you see it?
I see you need to, no, I see Zoom. I don't see the presentation.
Do you see it now?
Now? Yes.
Yeah, it's full screen, right?
Yes, perfect. Yes.
Okay, perfect. Then I start. Thanks, Pablo, and thanks everybody for joining us today. My name is Dulce Muñoz. I work as principal scientist at Funditec, and today I will present the work of Funditec in this project, okay, related to CO2. So first of all, Funditec, for those that maybe you don't know us, is a small private non-for-profit research center that is based in Madrid. We are in Spain, in the campus of the Universidad Autónoma de Madrid. And we are mainly focused to provide technological services to companies along Spain and Europe, and also to develop research lines that are mainly focused in 3 areas: in digital technologies, in agri-food technologies, and in the area of advanced materials. One of the lines, the research lines that we are developing today is related to the decarbonization and the circular economy. And as you know, in addition of being the coordinators of CAT Converse, we are also participating in another European projects that are related to the CO2 technologies, either the capture or the valorization of the CO2 by different techniques like Cosmos, Nefertiti, waterproof, and HiCAT. But today, as you know, we are mainly going to focus on the technology 4 within CAT Converse. That is where Funditec is working. And the objective of this technology is basically to convert the CO2 and try to contribute to the reduction of the CO2 emissions. And this conversion has the aim to obtain chemicals that are the cyclic carbonate, okay, that are sustainable materials that have application in the industry as plasticizer, as electrolytes, but are also useful building blocks in the synthesis of polymers and resins, like the polyurethanes that avoid the use of toxic substances like isocyanate. So for this, we're going to base our technology in a thermocatalytic process using porous organic polymer catalyst. We use these POPs, these organic polymers, because they have several advantages. They allow us to play with the design of the polymers and to achieve certain functionalities that we believe is going to help to coordinate to the CO2 and enhance this coordination and this affinity to the CO2. Also, because we can control the porosity of the porous organic polymers, and because they are very stable materials. They could be the base of our heterogeneous materials, heterogeneous catalysts that can be, after use, recycled several times, and also because they stand high temperatures. As I said, in this technology, the general aim is the conversion of this alkene substrate, okay, into cyclic carbonate. And these alkenes that we start with are present in many fatty acids and vegetable oils that are available in different biomasses like algae or vegetable that are usually in some waste agri-food, in some agri-food waste. Okay, so the idea is to do a technology that is able to, from these wasted materials, to obtain useful cyclic carbonates for obtain value chemicals in one pot to a step process. Okay, we aim to do a first oxidation step, okay, and without the isolation of this epoxide to be able to change the gas, the oxygen to CO2, and then carry out the second step, that is the carbonation. Okay, for this, our approach
it is the use, as I said, of porous organic polymers, and our polymer design is based in 3 families of polymers. There are, for example, polyaminals. We explore different chemical structures based on polyaminals, polyamines, and hypercross-linked polymers. So the first step after the design of the chemical structures, it is the synthesis of the catalyst. And this starts with building up the polymeric structure. So for this, we have combined and we have explored different aromatic amines, and we have also tested the difference on 2 different synthetic methods. We use solvothermal chemistry, and we also use microwave heating technology. So for in these 2 methods that we tested, we have already found differences. The main difference is the easy and the sustainability, because in the use of microwave synthesis, the times of reduce very much, okay, compared with the classical solvothermal. But not only in the method, also in the polymers that we obtain. We have observed that for most of the chemical structures, the microwave heating gives higher porosity into the polymers when compared with the same structures that are synthesized by classical solvothermal heating. With this technology, with microwave heating, we have obtained up to values of 500 square meter grams of porosity. The next step is the functionalization of these chemical structures, okay, to obtain our heterogeneous catalyst. And here we have selected 4 chemicals because of their abundance in the nature, and also because looking at sustainability, because, for example, iron, it is considered a sustainable metal, okay? And the aim, it is to introduce different quantities of the metal into the chemical structure. For this, we use this unit that is going to bind to the metal, and is also highly content in nitrogen, that is going to help the affinity for the CO2. And in this case, we obtain catalysts, materials that are containing different content of the metal, okay, from 0.5 to 5%. This is very much dependent on the chemical structure on the salt that we start with for the coordination of the metal, and also depending on the metal that we use. Okay. Once we have the materials, we have started for the carbonation step, okay, for the second step in our 1.2 step process. So in this case, we have tested different conditions, and we have tested different materials, okay? Different conditions, of course, like pressure, temperature, and the catalyst. More than 10 catalysts have been tested for many of the substrates that I show here. We started with styrene oxide. That is a very simple molecule, and it is much more easy to work with because it's not double substituted. And then we move on to another materials that are bio-based. Okay, they are derivatives of fatty acid and also vegetable oils. Okay, so from this work, we can say that most of the materials, although we have our preferred ones, but most of the catalysts achieve very good conversion, up to 90%, 97%, and good selectivity for this type of conversion. Okay, we have also proved the recyclability of this catalyst, what it is an important goal, an important fact. Okay. Talking about heterogeneous catalysts, and we show the good recyclability up to 5 runs. We then tested in other more complex substrates, okay, like for example methyl linolate epoxide, or as I said, vegetable oils, okay, which have more complexity, and here playing with the conditions, okay, but at relatively good and low pressures and times of reactions compared with the literature, we obtain conversion up to 90%. Okay, so the next step, it is to test the oxidation, okay, the first step. The traditional materials used for the oxidation are based on peroxide, okay, like methachloroperbenzoic acid or hydrogen peroxide. This technology doesn't match with the second step. So what we have explored here, it is a process that is based on the Mukayama oxidation reaction, that it makes use of another gas that is oxygen, okay? And we have tested different conditions of temperature, pressure, catalyst. You need to add a sacrificial material that is an aldehyde, okay? In this case, it's isobutyric aldehyde. And with this process and with our catalyst, we were able to obtain conversions up to 70%. So the final goal, it is to test the compatibility between the materials from the first step and the second step, okay? We want to keep, as I said, not isolate the epoxide, okay, to carry on the process and to be able to recyclate, okay, to do the recyclability. And we have demonstrated, okay, with some effort, okay, that the final conditions and the process can be achieved in one pot, two step, okay, playing with the temperatures, with the conditions. So the idea here is to take the reagents, to put oxygens. Once the oxidation is complete, remove the oxygen and replace it by the CO2, okay, and maintaining the catalyst in the two steps, okay. So these are the results so far. We are now moving on to the scale up. We are working now with our partner that is CCTech, that is building up a prototype that we will be able to test in a real current of flow of CO2, okay, in Perseo, that is the provider of the CO2, is the bio-based industry. And this is something that we hope that we can achieve and we can test in the next coming months. Okay, so this is a brief summary of the technology. I thank everybody, okay, for your attention. Also my colleagues in Funditech for the work. And if you have any question, I think there is some time reserved at the end of for this.
Thank you so much, Dulce, for this valuable presentation. Now it's time to present the last of the 5 technologies developing the CAD Converse project from Cartif. So Maria.
Hi, can you hear me?
Yes, we can hear you.
Okay, perfect. So I'm going to share my window. Do you see it?
Oh, not now. No, I see Zoom.
Okay. Wait.
If not, I can serve for you, no worries.
I can try once more.
Okay.
Just in case. Okay. Now I guess. Do you see it?
Not now.
Oh. Okay, then.
I will serve for you, no worries.
Yeah, thank you very much.
You let me know when you want to move the slides.
Perfect. Thank you.
Perfect.
Yeah.
So I guess you can see it, right?
Yeah, thank you very much. Okay, so thank you very much for your introduction, Pablo. My name is Maria Anderez. I work in Cartif as a researcher. And today I'm going to talk about the bio-methanol production from CO2. Next slide. Okay. Fundación Cartif is a technological center based in Buecillo, near Valladolid, in the northwest part of Spain. And our mission is to generate knowledge in order to transfer it to companies and to help them to improve their competitiveness and help them to adapt to the market. Next slide. It was founded 30 years ago, and since then we have been working in in national and international projects, and thank you to this, we have gained expertise in different processes, especially in producing value add from waste. Next slide.
Sorry, I do not see, I don't know if someone has the same problem, but we don't see the presentation.
Oh.
People is writing the same on the chat. Yeah.
You cannot see the presentation?
No. Sorry.
No, but thank you for
Giving
informing.
up tips on the chat.
Okay, what about now?
No, me either.
Oh, yes. Now you have Eva Maya presentation, looks like, or no?
No, this is, I see mine.
You see yours?
Yeah, yes.
Here in my Zoom, it says that you are also sharing your screen. So maybe if you stop it.
I can see that Pablo is sharing his.
Because there are two shared screens at the moment, Pablo's and Dulce's.
Now it should be work. Let me. Okay, now you can see this figure, right?
Yes,
Perfect.
yes.
Okay, thank you.
Maybe
Thank you for
need-
informing me.
Okay, well, I will continue from here. So, okay. Regarding the background that I explained before, that converts fits in our philosophy as the project aims to convert wastes into useful products. So, click, Pablo, please. Cartif is responsible in producing bio-methanol from CO2, converting it through metallic catalyst and supported over aluminum fibers at moderate pressure and temperature. Next slide. Okay. Why biomethanol? Because it is an unuseful product that can be used in a wide application of applications. Sorry. From cleaning to precursor of other chemicals and as hydrogen storage or carrier, and thus it can be used as fuels. Nowadays, the production of methanol is from in the industry is produced or based in fossil fuels, and there is a need or there is a search in finding another raw material based on CO2 normally. Why CO2? Because it is an abundant material, it's a waste, and also it can help to reduce the emissions and level of CO2 in the atmosphere. However, this conversion is difficult because CO2 is a very stable molecule and it requires a high input of energy in order to be transformed. It can be done by adding active molecules such as hydrogen, alcohols, also with the aid of a catalyst or at high temperatures and pressure. This reaction is also exothermic, creating hot spots in the reaction bed, thus modifying the selectivity and conversion of CO2, and it should be controlled. Normally, this conversion should be is done using catalysts that improves the kinetics of the reaction. These catalysts are based normally in noble metals such as ruthenium, iridium, gold, achieving outstanding results, but they are very the cost is high. There is then a necessity to switch this or substitute this metal by non-noble metals in order to achieve acceptable activity but at lower cost. In addition to the cost of the metals, there are additional operational costs related to the high pressure required for the conversion of CO2. That due to the compression of these gases to the operational pressure. In order to avoid this cost, there is an alternative to increase this partial pressure in the surroundings of the methyl catalyst. Next slide, please. So Cartif, in order to overcome these problems in the CO2 conversion, has designed, synthesized, and evaluated a catalyst for this reaction. First of all, the metal selected for the conversion has been chosen between in a mixture of copper and zinc because they are active and cheap species for the hydrogenation and moderate hydrogenation of CO2 at moderated temperature and pressure conditions. And these metals are supported over aluminum fibers. This fiber has two functions. The first of them, they will provide aluminum moieties that also contribute to the CO2 conversion, and also these fibers, due to the heat conductivity, can dissipate the heat generated during the CO2 conversion. In addition, we have synthesized hydrotasite, that is a type of synthetic clay that can absorb CO2, favoring the CO2 conversion and methanol productivity in the surrounding of the metals. Next slide. So these materials have been prepared at Cartif by different methods. In the case of the aluminum fibers, they have been shaped into chips that can fit in the reactor afterwards, and these chips have been treated and impregnated with the metals and different processes in order to achieve the best catalyst. These catalysts later have been characterized by different techniques in order to determine the chemical and physical properties. And finally, these chips have been treated in a pilot plant in order to determine their activity and methanol production. Next slide. So during this time, we have designed and synthesized an active catalyst for the methanol production, achieving almost 500 grams of methanol per gram of copper an hour as a production rate. The reaction conditions have been also investigated, achieving a reasonable activity at low pressure and low temperature, lower than the one reported in literature. And also we have observed that the hydrotalcite have improved the methanol selectivity and production when it was added to the catalyst. Also, we have been tested the catalyst at long-term reactions and on-off cycles, showing a stable activity, being able to be used in on-demand processes, for example, for the CO2 conversion using hydrogen produced by renewable energies. For the following year that will come with the project, we will investigate the reaction also in a continuous pilot plant that has been modified in order to introduce a recirculation in order to improve the results of selectivity, methanol production rate, and conversion of CO2. Click, please. So all in all, during the CatConvert project, Cartif has designed and developed a stable catalytic system able to produce methanol at a low energy consumption in order to be upscale to the industry. So thank you for your attention. So if you have any question, please feel free.
Okay, thank you so much, Maria. I think I don't see any question. I see one raised hand, but I cannot give you permission to talk. So if you have any questions, you can enter in the chat. Since now I didn't see any questions from the audiences. But if not, remember that you can also follow us on social media. Oh, we have now the question from several questions. So the first one is what IA the oxidation state of Cu in your composite? I don't know who can take this question. You can see the speakers in the chat.
I don't know if it is for bio-methanol. So I will answer, otherwise, please. In the case of the catalyst synthesized here at Cartif, when synthesizing it, it is copper 2 plus. But when we prepare it when we set it in the reactor, there is a reduction process before going to the CO2 conversion. So when it is for the CO2 conversion already, it is copper 0.
We have another question just concerning the slides. Is it possible to receive the presentation? The answer is yes. I will upload it to the CatConverse website, and I encourage you to follow us on social media because I will probably launch a special post informing you that all the materials, the recording, and the presentation will be available in the CatConverse website. We also have another question for you, Maria. Thank you, Maria. Can you provide some details about the preparation and characterization of the fibers?
Oh, okay. I don't know if we have time. I will try to be fast. The fibers are commercial ones. You can buy it in from several providers. Then we just wet it and shape it in a dye, and then they are clean, following some literature that you can find, in Google academic or whatever. And they are clean. They are then oxidized by different processes, and afterwards they are calcinated and then impregnated, and then following the reduction process and that I was explaining in the previous question. You're welcome.
Okay, so it seems there are no more questions. And as I said, if you have any more questions, remember that in our website, we have a contact form where you can reach us in case you have any particular interested in any of the 5 technologies presented today. From my side, it has been a pleasure to host this webinar, and I would like to thank all the speakers of today for joining in this webinar and present the status of their technologies. As I said, I invite you also, I would like to thank all the attendees that have joined to the webinar. And remember that, as I said before, you will have the recording and the presentation probably beginning of next week in the CatConverse project. So from my side, just want to thank you one more time, all of you attendees and also the speakers. And I encourage you to stay tuned to our social media to know more about the progress of the CatConverse project. So thank you so much.